Okay, so probably we can start. I'm Fabrizio Mo, the chair of IEEE Student Bench PoliTo. I'm very glad to be here today and to see that the room is almost full. That means that the event somehow had success among the students and so on. Just a few words before starting. The IEEE Student Branch PoliTo is an association, official association of the IEEE. It is composed by students who are also IEEE members. And our mission is to promote the sharing of knowledge among different levels. That means linking professors to students and also linking students to companies, to firms. And we would like to share knowledge for the pleasure of sharing knowledge, but also for creating a network such that students can find their way in the future job world, let's say. Today, as you probably know, there is the final event. This is the final event, so there is the final presentation of 2 selected papers. These papers were written by students and they are about works that they did during maybe thesis works, during maybe laboratory and projects here at the Politecnico di Torino. And this is the program. You can find the program also on the flyers that you have on the chairs. You can also use the QR code to follow us on social networks and so on. So if you like, if you enjoy this event, I will ask you to simply follow us for next events. This is the program. We have at the beginning a short talk by Professor Martina, and then there will be the presentation of the 2 selected papers. These papers were selected through a review that was performed by researchers, PhD candidates and professors of the Politecnico di Torino, of the Department of Electronics and Telecommunications and the Energy Department. And these 2 works were selected with these reviews that were anonymous on both sides. And now there is this final presentation. If everything goes fine, I hope so, probably we will assign the final awards to these 2 papers. And in that case, it means that they will be automatically proposed to the student paper contest of the Region 8 of the IEEE, that includes Europe, Africa and Middle East. So it's quite big amount of countries, okay? And if they will be selected, they will be presented in an IEEE international conference that is Melecon 2024. So it's very important, because this conference is a serious IEEE conference in which papers of researchers, of professors also are selected by peer review. And so this is a good opportunity for the students. I hope maybe they will have this success, and this could be a good opportunity to present their work and have a good visibility. So now I will leave the stage to Professor Maurizio Martina. Thank you.
Alright, so just a few seconds for the setup. Alright, okay, here we are. Now I should find my slides. Alright, okay, right. Yes, it's working partially. 3, 2, 1, let's go. All right, great. So good afternoon, ladies and gentlemen, welcome. I'm very pleased to be here today. I see a lot of already known faces in the audience today, and very glad about that. And so, my name is Maurizio Martina. I'm the counselor of the IEEE Student Branch here at Politecnico di Torino, but I'm also a teacher, so I'm teaching mainly digital electronics. So my field of research and of work is the field of digital integrated circuits. And what I want to tell you today is something about one of the main research line that I'm trying to carry on about RISC-V centric accelerators. Okay, so a few words about that. Okay, well, maybe not everybody in the audience knows what RISC-V is, and RISC-V is an open standard instruction set architecture that's been developed mainly in Berkeley at the beginning of the time with the idea of enabling a new era of processor innovation through open collaboration. And then, starting from Berkeley, this project has been developed roughly on all the planet, but mainly in some part of the planets. And currently, there is a lot of interest in RISC-V development in Europe. So just to give you some ideas about what in practice RISC-V is becoming, we have open hardware models. So hardware description language models that are providing you with the model of a RISC-V processor, of a RISC-V platform for working. They are free and open. As an example, probably the most famous one are the ones developed in ETH Zurich, that is PULP platform, and the one developed in EPFL, that is the XIP platform. But there are also other platforms developed at Berkeley or other research and university institute around the world. I think that these two are the most famous one. They are open not just from the hardware point of view, that is of course interesting and important, but you know, when you try to develop from scratch microprocessor, one of the main bottlenecks that you find is that then at a given point people must be able to use your processor. And since nobody today is happy to write assembly or machine level code, you need also some other elements that are easing the use of your processor, that are mainly two aspects. Interfacing the core with something else. So if you want to design an accelerator, you need to know how to interface your accelerator to the core. And then the compiler. And so you need a tool chain for programming, probably in C or in kind of a high-level language for programming typical cores, and a compiler. And these things are also available within the RISC-V environment. So there are open interfaces for interfacing accelerators to the core, like OBI and XIF. And from the software point of view, there is the Open GNU toolchain, so you can write your C code, you can compile it by choosing RISC-V target, and so you can run your application on RISC-V, and you can also exploit some extensions and some accelerators, some other elements that can be extremely helpful, especially if your purpose is speeding up the execution of a certain application on a RISC-V platform, right? So this gives you an idea of what RISC-V is. But before going into some technical details about the use of RISC-V for building kind of RISC-V based accelerators, I want to stress the importance of this aspect, RISC-V in general, but more broadly, the importance of microelectronics today. Indeed, as you probably know, there are European initiatives related to the development and the fostering of microelectronics in Europe. In particular, there is the European Processor Initiative that is very closely related to the RISC-V implementation, and there are also some RISC-V related projects. Probably the two main ones today are Tristan and Isolde. There are two projects funded by the European community, and fortunately, as Politecnico di Torino, we are involved in both of these projects together with ETH and Unibo, the Open Hardware Group, and plenty of companies like Leonardo Engineering, ST Microelectronics, NXP, and you know, a lot of big players. So I think it's very interesting today being involved in this kind of project. And then I decided to spend also some words about local initiatives, Italian initiatives in particular, as we have a very interesting initiative that is the Industrial PhD Program of National Interest in Micro and Nanoelectronics that is coordinated by University of Pavia, and this is the collaboration of a lot of Italian universities. Here you have the full list with all the involved people. I think this is a very interesting opportunity, in particular due to the fact that last Friday, on the 3rd of November, has been part of this initiative of this national PhD program, have been invited in Pavia for the kickoff of the Fondazione Chips.it. That is a very important aspect again related to the initiatives that are available within Europe, but more in particular within Italy, about microelectronics design and development, and in particular for what I'm going to tell you in a while about RISC-V related architectures. Okay? So now going back to RISC-V, what can we do with RISC-V? Well, as you can imagine from what I told you so far, we can develop a lot of things. So one of the interesting points related to RISC-V is that it's enabling new possibilities, new applications. And so depending on your imagination and on what you think is interesting and what is worth being studied today, you can try to develop it by relying on RISC-V. And so this is the focus of my today talk. So I want to show you two main applications that can take advantage of RISC-V that are security applications, in particular the post-quantum cryptography ones. In particular, I will give you some very small details about the lattice-based schemes for this kind of cryptography, and then artificial intelligence, or AI, and more in general machine learning, ML applications, with a specific focus on convolutional neural networks at the edge. Right? So let's have a look, starting from the first one. I think that you know what cryptography is, but maybe you do not know what post-quantum cryptography is. So post-quantum cryptography aims to create and build quantum-resistant cryptographic schemes by exploiting some kind of hard mathematical problems that cannot be broken by quantum computers. Okay, so it's not kind of science that is relying on quantum computing, but it's something that wants to be resilient against quantum computing. Okay, so if you imagine that in I don't know 10-15 years we will have quantum computers around the world, we have the problem that today cryptography systems are not strong enough and they can be broken pretty easily by a quantum computer. And so that's the idea. Once quantum computers will be available, we need cryptographic schemes that are robust against the power of quantum computers. All right, so this is the main idea. And so another element that we have to clarify probably before starting going into the details is the concept of a key encapsulation mechanism. That is pretty simple idea that is already used today, but with schemes that are not robust against quantum computer. Now that means having a sender that encrypts a secret key with the public key of the receiver and sends this ciphertext to the receiver. The receiver receives it and decrypts it with its private key in order to recover the secret key, right? So this is a general scheme that is independent, completely independent of the fact that we are relying on traditional cryptography like DES, AES, or whatever, or relying on post-quantum cryptography. And it becomes particularly interesting if we think of something that goes in perspective. So being robust and resilient against quantum computers. Okay? So this is kind of broad range of ideas that stems from something that happened, let's say, from 5 to 10 years ago at the very beginning, where the National Institute of Standards and Technology started the processing for standardizing post-quantum cryptography algorithms. And after a set of rounds and a lot of discussion, last year they selected among the finalists one very interesting system algorithm that is called Crystal Kyber. That is a lattice-based CAM, and so it relies on the fact that it's particularly hard to solve one, let's say, mathematical problem, that is the model learning with error problem. Okay, so without going into the details of mathematical details of this scheme, we can try to provide some information about what's happening if we try to accelerate this algorithm by relying on some hardware and some software. So the main problem is that the implementation of this kind of algorithms, being relatively new, has not been studied too much yet, right? And so we have to study how this algorithm perform on a microprocessor and how they can be accelerated, which are the bottlenecks and which are the parts that is important trying to accelerate in order to achieve significant, or let's say enough performance for a certain application, right? One of the main elements within Crystal Kyber is catch. That is a cryptographic hash function based on the sponge construction, okay? Where the input bits are divided in blocks, and then there is a special permutation that is applied to these bits in order to create the encrypted version. And then another element that is very relevant in the context of Crystal Kyber is the numeric transform, theoretic transform, sorry. That is a special case of the discrete Fourier transform that relies on integer representation. So it's built in a finite field that is made from ZQX, right? And trying to integrate the implementation of this algorithm on a RISC-V platform is something that can be interesting. So we are focusing on the integration on a very specific platform for RISC-V, that is Palpissimo, an advanced 32-bit microcontroller with single RISC-V core that has been developed by a joint group between ETH and University of Bologna. And the interesting result that we obtained in this field is that we were able to develop an accelerator that is called Loki, that is interfaced with the rest of the system through an AXI bus. And here you have some detail about the inside of the accelerator. You see that we have some core and then some interfaces in order to adapt the data stream between the AXI interface and the internal representation of the core. But let's go to the result, that is probably the most interesting part. By relying on a pure software implementation, so running a C model of this Crystal Kyber algorithm on pure RISC-V platform, we have a number of cycles that is pretty large, as you can see in the first column here. Oh gosh. I should have the pointer somewhere, probably, hopefully. Where's the pointer? Here's the pointer. All right. Here in this column, you see the result in terms of clock cycles in the pure RISC-V implementation. While if we rely on the hardware accelerator, as you can imagine, we can obtain better performance. How much better this performance are is shown here in the second and the third column, in particular the last column. The third column is showing you the improved factor, trying to compare the runtime between the pure RISC-V software implementation and the one with the, let's say, advanced RISC-V implementation, including Loki, that is a mix of hardware and software implementation. Okay. Another point that's pretty important when you try to accelerate something is trying to keep under control the complexity. And so this table here is showing you what's happening if you try to implement the proposed platform on an FPGA, and you see that we have that the amount of complexity is still kept relatively small. So at the end of the story, it works the way. Accelerating this kind of algorithm on a RISC-V platform as you can achieve a lot of increase in terms of performance with a moderate area overhead. Right? Another thing that I want to tell you is trying to exploit a similar approach but for a different application. So what's happening if we try to concentrate on artificial intelligence and machine learning applications, in particular convolutional neural networks on a RISC-V platform. So for this kind of application, we concentrate first on one aspect that is pretty simple but also very important within this kind of application. If you, I don't know if you know, maybe you know, a convolutional neural network is mainly an element that is performing a lot of convolutions. The convolutions at the end of the story are kind of products between matrices. So we can simplify the thing in observing that convolutional neural network requires to perform a lot of multiplications and accumulations. So accumulating the results of the multiplication. That is in practice what's happening when you are making the product between two matrices. Okay? So the interesting thing is that in general, convolutional neural network, but neural network in broad sense, are relatively robust to pruning, quantization, and arithmetic approximation. Pruning means that instead of considering the whole network with all the weights, we can remove some weights here and there, probably the ones that have a very small magnitude that are probably less relevant to obtain the final result of the network. Quantization, so the number of bits that we are employing for representing the quantities inside our neural network. And approximate arithmetic, meaning that maybe if we are not performing the arithmetic operations in a precise way, we still obtain something that is useful. In particular, since neural networks are not able to obtain 100% of accuracy, maybe a very high accuracy but not 100%, we can tolerate a small reduction in the accuracy of a neural network by relying on the fact that we are not performing the computation in a perfect, correct way. Stupid example, if we have to perform a multiplication and we are skipping the least significant bits of the result, we are introducing an error in the result of the multiplication, but maybe this error is not much important for the application, so it's not affecting too much the accuracy of the network. So this is the idea. And so what we tried to do in this field was to try to keep a RISC-V platform with an approximate unit for performing approximate multiplications. One thing that is pretty important and in my opinion also interesting related to using approximate multiplications within a RISC-V platform is that you have to pay attention to the fact that if you're performing multiplications between data and so you are introducing an error on the data, this is not maybe important, or from another perspective, this is exactly what we want to study. But you have to consider that inside an application, you might perform multiplications also not between data, but with other quantities like indices or addresses for computing a new address. And introducing an error in this kind of computation can be extremely dangerous as it might impair completely the application. So you have to find a way to discriminate between multiplications between data, so something that can be approximated, and multiplications between non-data, so something that shouldn't be approximated at all, right? How can you do that? Well, you have to instruct the processor that at a given point you have a multiplication that can be approximated or a multiplication that must be not approximated. And this can be done by relying on some registers that are configuring on the fly the microprocessor. And that's why we have these CSRs inside of the architecture. Okay? So let's go to the result. What's happening in practice? The result is pretty interesting, and I don't know if you can see it. Yes, it's partially visible. Here, this graph is showing you what's happening with different topologies, so with different networks, with different data sets, and it's showing you that if the perfect network is this one, here you have one network, here another network, they are all taken from ResNet, but with a different complexity, okay? So these are the, let's say, the reference, the perfect results of the network. And here you have what's happening if you are trying to introduce some errors in the computation of the multiplication. You see that it's pretty interesting to observe that you can introduce a relatively large amount of error, and the accuracy of the network remains nearly the same till a certain value, but as you can see, even when it decreases, it's not decreasing too much. But on the other side, what you can see here on the y-axis is that the energy reduction becomes really important. So looking at the x and y-axis concurrently, what happens is that we can reduce pretty much the approximation level without impairing too much the accuracy, but the advantage we have is that we have an important energy reduction. And so that can be very interesting element, especially if you're trying to implement convolutional neural networks at the edge, so on a platform with small amount of energy available, small energy budget available, okay? Right, so I don't want to waste you too much time with my blah blah, and so I want to finish simply thanking all the people who work with me and who contributed to the work that I presented you. Thank you so much.
Okay, so thank you again, Professor Martina. I would like now to invite the first presenter of today, who is Vincenzo, please.
So good afternoon, everybody. Seeing a lot of people here in this room fills my heart with joy. So thank you for being here and using your time to attend this presentation. So this work, I'm Vincenzo Petrolo, a student here at Politecnico di Torino. And this work was done in a team with other 3 people, Alfredo Paolino, Pugliana Asgari and Simone Ruffini, as part of the SOC verification workshop, which was held last year here at Politecnico di Torino. The title of our work is UVM Software-Driven Verification of Pipeline Risk Microprocessors. So it means we are going to talk about verification. But before going into the details of this work, I first want to take a step back in the computing history, and in particular I want to talk to you about the Intel division bug that was found in the floating point unit. So it was a very significant error which costed a lot of money. An estimate counts it for almost $500 million, and the error also costed a lot in terms of reputation for Intel. Therefore, since then, the companies and the chip industry has focused a lot and put a lot of effort into building effective test benches that could verify the correct functionalities of a microprocessor and that could catch bugs before going into production, so that they could prevent this error from happening again. And this trend of putting a lot of effort into verification has kept going on till nowadays. And this is assessed by the news we find on the newspapers. So we can see here Cadence in 2021. This is for medical technology application in 2022. And this is 2021 again. But most importantly, what I want to show here is this plot that is showing the verification costs as compared to the other the design phase during the chip design phase. So we can see here the development costs going from left to right, are increasing for all the architecture, software verification, and physical phases of the chip design, but the verification is the one that is increasing a lot compared to the others. And this raises a fundamental question, that is, how can we actually mitigate the verification costs? So currently the state of the art is UVM to do so. UVM stands for Universal Verification Methodology, which was born in 2011, and it is currently being maintained by Accelera, which you might already know. Moreover, it is a framework built on top of the System Verilog HDL language, and it recently became standardized by IEEE as one of its standards. Moreover, the UVM framework has three important characteristics that are reusability, flexibility, and a very stable standard, as I was mentioning here for IEEE. And what UVM does is basically it provides you components that can help you in verification, and they are actually sending random stimuli to the design under tests that could uncover bugs, and it is at the same time monitoring on the output of the design under test to catch if some error happened. And the power of the UVM framework is that we can actually, by changing the interface component, which is a very small component, you can actually reuse it to test another design, thus saving a lot of time and avoiding recreating from scratch another test bench for verifying another module. So that's the power of UVM. But what we want to answer today is, can actually it be used for microprocessor verification? And the answer turns out to be no, or at least it's not that easy to do so. And let's see why. A microprocessor has a lot of internal states. Just think to the finite machine inside the control unit, think to the number of registers. And that combined to the number of inputs of a microprocessor make the overall complexity unmanageable for a standard UVM test bench. Moreover, to make the situation worse, the controllability of a microprocessor is very low because we can feed it only with valid instructions. And the observability of it is low as well because we can only look on the data bus to see if there are errors coming out of the microprocessor, which means that we cannot probe inside it and look for bugs happening inside the microprocessor. So some errors might also be masked and we could never catch them. So the answer to the question we wanted to answer, sorry for the repetition, is that the standard UVM test bench is not the solution. And in this work we are proposing a solution that is founded on four main pillars. Reusability, which means that our proposed methodology should be applicable to any microprocessor. Clearly, our solution should be cheaper in order to decrease the verification costs, which I was talking about. Moreover, our solution follows a bottom-up approach, which means that first we verify the correctness of all the sub-modules of the microprocessor. For instance, coming back to the Intel division bug, so that was due to a lack of verification in the verification functionalities, verification process on the floating point unit. Due to a low extent of verification in that part, the error was caused. So a bottom-up approach could actually increase the confidence we have on the final results. And last but not the least, our solution is UVM-centric, which means it is based upon a standardized kind of test bench that can actually effectively catch bugs, as we will see later in this presentation. So these are the four main pillars, and let's take a look at what is the solution, the methodology. So the methodology is a two-phase verification strategy. We first start at the bottom level with the module level verification, where we test the correctness of each and every microprocessor subsystem. And only at the end of the verification, once we are sure that those modules are correct, we are ready to move on to the next stage, that is the chip level verification. Here, as you might think, we are not sourcing the microprocessor with random instructions anymore, because we cannot do that. As I was mentioning before, we can only give it valid instructions. And therefore we rely on the usage of a combination of meaningful C programs and random assembly programs. And I will later explain why this is especially important in our approach. Moreover, we measure the comprehensiveness of our methodology by means of code coverage and functional coverage. The code coverage measures the amount of code, of RTL code of our microprocessor that is executed during the simulation, which tells us more or less how much of the code we covered, and therefore it allows us to understand if our verification is complete. And the functional coverage instead measures the percentage of the tested functionalities. So let's say our microprocessor has 100 functionalities. We want to understand if we tested all 100 of them. And therefore this helps us in understanding this. And by combining those two metrics, we can actually make sure that our verification is complete or not. So let's focus on the module level verification. The module level verification has two fundamental benefits that were the ones missing in the floating point unit of the Intel that happened for the Intel Pentium processor. So the first benefit is easier bug localization, because if we test a module, a functionality at the module level, if we have a bug, we already know where to catch it, where to look at for fixing it. And the second benefit is that it is easier to test all the functionalities of the module. Think of an arithmetic and logic unit. It will be much easier to enumerate all the possible functionalities of that unit rather than simulating it at the chip level with instructions. So it would be much harder to do that. Moreover, since our solution is UVM centric, the usage of UVM allows us to generate test benches in a faster way. So we can see here we have a UVM test bench for module 1, for module 2, and so on. So we can do this very quickly thanks to the reusability key characteristic of UVM. And last but not least, since we are using UVM, the constrained random stimuli that we are providing to the modules actually could uncover potential bugs that were left uncovered during the design phase. So we might find bugs that we didn't think about while developing the design. Therefore, we can conclude that the module level verification is essential for establishing the correctness of the chip at the system level. And therefore, let's introduce the most important part of our approach, that is the software-driven chip level verification. So our goal here is not to test the modules anymore, but to test their interconnection and their communications. Therefore, we want to test the synchronization of pipeline stages in our microprocessor, to test the combinations of the instructions concurrently being executed in the pipeline, and the communication protocols with the external peripherals. And to do so, we have to customize a bit the UVM test bench. So the first example is here in the sequencer. In a UVM environment, usually the sequencer sources random instructions. But here we instead customize the sequencer to contain an instruction memory, which is provided with the program counter. And by doing this, we can actually offload most of the complexity of the communication with the instruction memory into the UVM test bench to make the simulation much faster, and also to decrease the overall complexity of verifying also the instruction memory, because the instruction memory could have bugs. Then the sequencer will source an instruction at each and every clock cycle thanks to this program counter, and it will drive both the microprocessor and a golden model of the microprocessor, which are concurrently being executed and which outputs are compared inside the scoreboard. So the scoreboard is a fundamental UVM component, and if the two outputs are mismatching, then it means we have a bug. So the usage of this kind of test bench can actually raise a question, that is, which kind of program should be executed to verify the microprocessor? So we tried to answer this question in our research, and we explored two possible ways. The first one is by using meaningful C language test programs, which means we develop a C language test program with some algorithm, then we compile it, and then we run the assembly code on the microprocessor. This actually has two benefits. That is, the first one, that is easy and fast to write a C program rather than writing its own assembly. The second one is that by doing so, we can actually port this program to any microarchitecture and increase the reusability of our methodology. However, there is a fundamental drawback here, that is that due to compiler optimization and due to the programming language conventions, we are actually decreasing the controllability, because the compiler generates an assembly code that is optimized to use always the same set of instructions and always the same set of registers, and therefore it doesn't guarantee comprehensive verification of our microprocessor. Therefore, this is the reason why we moved to a second solution. And the second solution is to use random assembly programs, but they are not fully random in practice. So those random assembly programs are automatically generated by a software we developed, and these programs are inspired by software-based self-testing. Software-based self-testing, also known as SBST, is actually used for fault detection. And because of that, it is particularly useful at stimulating most of the design and to cover those holes which were left uncovered during the meaningful C language test programs. Therefore, at this stage in the research, we thought that these two approaches could be combined together to make and improve the software-driven verification process. But we could not stop here, and we had to actually demonstrate that our methodology was effective. And we did this by applying it to an actual microprocessor, which is the ELX, which is a 5-staged RISC microprocessor, which is also pipelined. And again, we used the code coverage and functional coverage metrics to assess the verification completeness, but also here I'm showing you a set of benchmarks we used to run the software-driven verification phase. This phase, these benchmarks, the first three, so these three, are actually written in C language. This is a simple iterative division program, this is a bubble sort program, and this is it is called iconics because it's a set of complex algorithms such as quicksort, matrix multiplication, recursive functions, and so on. And thanks to this, it was very easy to write those programs and to actually generate an assembly version of them. However, what you can note is that the low number of instructions variety, which means there are low amount of colors in these columns, because we are always using the same set of instructions due to compiler optimization. However, if we use the SBST, which is random assembly program, we obtain larger instruction variety, as you might note here in this column. But it has another drawback, that is that the random assembly program are missing complex control flow instructions, which instead are present in the iconics benchmark. So again, we wanted to merge and to get the best of the two worlds, and to do this we combined those two test programs to generate a final test program which was the suitable candidate for our verification phase. And with very little of imagination, we called this program Frankenstein, and it has a lot of instructions variety, whereas at the same time has a very complex control flow of instructions. So with this we can actually start our verification process of the ELX microprocessor. But before delving into the software-driven verification, we first have to verify the modules. So at the module level, we divided the pipelined microprocessor into different stages, and we verified them, and we found 100% of functional coverage in the verification process. And also we found a bug into the adder of the arithmetic and logic unit, which probably we could have not found if we had run the verification directly at the chip level, because it was due to, like in the Pentium division bug, it was due to a simple set of numbers which were actually resulting in incorrect addition. Therefore, by doing so, with just a very small set of random test sequences, it was easier to find a bug rather than if we had applied it with directly at the chip level. So at the chip level, the key takeaway of this is that at the chip level it would have much more difficult to find this bug. And the 3% of missing code coverage actually, that you can see here, is due to a reachable code, which is basically could be just executed only due to faulty conditions of our microprocessor, which means after being in case of physical faults that could be bit flips, for instance. Therefore, after running this module level verification, we moved on with the chip level verification, and we executed all the 5 benchmarks we have on the microprocessor. And what we found is that, as we were expecting, the Frankenstein benchmark obtains the highest results, that are 100% of functional coverage of all the functionalities of the microprocessor and 93% code coverage, which is a lot if we think of the code base of the EDLX. Therefore, we conclude that the hybrid software approach actually improves the verification process. So this is the conclusion of the presentation, but before closing, I want to list our contributions here. So we have seen in the beginning that the extensive microprocessor verification is still a matter of research, as I was mentioning before with the news that I found on the internet. And to address this problem, we are proposing a 2-phase verification strategy that can be applied to any RISC microprocessor. So granting very high reusability and decreasing a lot the development costs of the verification phase. This solution has 3 main characteristics that are it is bottom-up, it is software driven, and therefore it enhances the portability of our solution, and it is UVM based, which inherits all the functionalities of UVM, such as reusability, flexibility, and good standardization. And the case study we demonstrated actually reached very high results. But of course, this work is far from being perfect. We are already working on future versions of it, such as generating shorter programs, both high-level and random assembly programs that could decrease the overall simulation time while still delivering these higher numbers, if not higher than this. And for those of you who want to further delve into this world, I am leaving here a few references for you, so you can actually read more about it. And also our emails, if you have any further technical question when you want to send us an email. So this is the very end of the presentation. Thank you for your attention, and feel free to ask questions if you have any.
Okay, perfetto. Good morning, everyone. I'm Eva del Carretto, and I'm here to present my thesis work. It is related to the assessment of stress and mental workload through eye movements analysis and processing. I'm part of the group eLions, and my supervisors are the professor Danilo De Marchi, the postdoc Irene Buraioli, and the PhD student Gabriele Luzzani. At first, a fast overview of what we are going to speak about. At the beginning, the problem introduction and the research objectives, then a brief part of state of art. Later, I will speak about the test session I carried out and the signal processing and the feature extraction. Later, I will speak about the results and the statistical analysis of them. And finally, the conclusions and the future steps. My thesis work is related to the HMI systems, so human-machine interaction systems. They are technologies where there is an interaction between human and machines, and in order to achieve a goal and to perform functions. Sometimes happens that the human has more tasks to carry out because of this interaction with the machine. This means that the stress and the mental workload he perceives are higher. Of course, if they are too much high, could be that there are unuseful risks and accidents. That's why it is important to measure and control stress and mental workload levels. And in literature is shown that we could do this using biosignals. Some of them are, for example, the signal coming from the body temperature, or for example the ECG, but also the signal coming from eye movements. And it is this signal that I studied in my thesis work. A brief part of state of art. At first, what is stress and what is mental workload? The stress is a discomfort feeling. For example, a person that is speaking in public is under a state of stress, while the mental workload is an overload feeling, a mental fatigue. So a person with a high level of mental workload is a person that is performing different tasks at the same time. Speaking about eye movements, there are two main kinds of eye movements. The first one is the fixational eye movements. We have them when we are staring to something. Of course, the gaze is not fixed, is not stable, but there are some micro movements. For example, the saccadic intrusions. In the picture, we can see them in yellow, the fixations, and in blue, the saccadic intrusions. The second kind of eye movements are the saccadic eye movements, and they are the ones in purple in the picture. They are rapid, jerky and ballistic movements where the gaze moves from one point to another. Of course, we needed to acquire these signals, and we did this with an eye tracker. This eye tracker is the Tobii Glasses 3, that is the gold standard. I began with a test session where 64 volunteer participants were enrolled, and the age interval is 18 to 40 years old. And speaking about the gender, they were quite balanced. At first, the trial began with a relaxation phase of 2 minutes because we needed to acquire the baseline. And then we continue with the Stroop test. The Stroop test is a test designed for creating different levels of stress in the participants, and there are 3 levels in particular of Stroop test, from the less stressful one to the most stressful one. Later, the participants had to do another phase of relaxation, followed by the NBEC tests. The NBEC tests are tests designed for creating different levels of mental workload in the participants, and there are 3 different kinds of them. The first one is a visual NBEC test, where the task is just visual. Then there is an auditive NBEC test, where the task is just auditive, and finally a dual NBEC test, where the task is both, so visual and auditive. Finally, there is the last relaxation phase, followed by the questionnaire. So the participants were asked to fill in a questionnaire where they had to match this one score from 1 to 3 with their subjective perception of the stress and the mental workload of each level of each test. With these 64 signals, I did a processing of them and then a feature extraction. At first, I identified the blinkings, so when a person is closing his eyes. Later, I identified the saccades with 2 thresholds, one on the amplitude and the other on the time. What was not a saccade was a fixation. And inside the fixation, I identified the saccadic intrusions, even here with the double threshold. From all these eye movements, I extracted the features. They are 23 in total, and they are, for example, the lasting and the frequency of each of these eye movements, but they are also coming from the frequency analysis of the signals. So they are coming from the power spectral density. There are also features coming from the pupil diameter, because Tobii Glasses 3 gives me directly the data about the pupil diameter. 50% of these features are already investigated in literature, while the other half were never investigated before. Here there is the flow chart in order to achieve the results and the statistical analysis of them. We began for each feature with a macro data set with the values of that feature of 64 participants in each level of the tests. We divided this macro data set in 4 data sets, one for each test. So for example, for the Stroop test, we had the relaxation phase and the 3 levels of Stroop test. The same is done for the other 3 NBAC tests. Later, I normalized on each participant through the Euclidean norm. And later I performed the class division. Class division is done on 4 classes. In particular, class 0 is given by default to the values in the relaxation phase, while class 1, 2 and 3 are the altered states, and they are given according to the answers of the participants to the questionnaire. Then I did a dataset investigation, so I plotted box plots and mean and standard deviation. Here in the pictures we can see 2 features. The first one is the velocity of saccadic intrusions, and we can see that the values of these features, of this feature in the class 0 is really different from the values in the other 3 classes. So this could lead to the conclusion that this feature allows a binary classification. Of course, this will be confirmed by the statistical analysis. The second feature is the blinking lasting, and here we can see that there are no differences among the 4 classes. This means that the binary classification through this feature is not possible. Finally, we performed the statistical analysis through Kruskal-Wallis test and Mann-Whitney U test. In particular, the first step was the performing of a Kruskal-Wallis test on the 4 classes, among the 4 classes. If the result of this test was a p-value smaller than 0.05, this means that at least one couple among the 4 classes gives me a significant difference. Later, in order to have a greater granularity of results, we performed the Mann-Whitney U test, in which we did the same. So if we did this test on all the 6 pairs possible among the 4 classes, and if one pair results to have a p-value smaller than 0.05, this means that there is a statistical difference between the 2 elements of this pair. This is the discussion, so the results of the statistical analysis. The first table shows the binary classification results. In particular, the last row gives me the number of features that allow a binary classification over 23 features in total. Binary classification means that we have a statistical difference between class 0 and class 1, 2 and 3. So we can distinguish between the rest state and the altered states. So we can conclude that 83% of the features allow a binary classification in at least one dataset, while 40% of the features allow a binary classification in all 4 datasets. The second table shows the overall results. Here we can see that a greater granularity of results is more difficult. Finally, the conclusions are that the ocular signal, as we could see, is very sensitive to variation in stress and mental workload. The majority of features that I extracted allow a binary classification, and of course a greater granularity of results is more difficult. Moreover, the new features that we investigated, that were more or less the 50% of them, of the total, are promising, so they worth to be deeper investigated. The future steps are the implementation of these results with the results coming from the other biosignals. This in order to build a model for discriminate stress state and mental workload state from the relaxed state, and this for developing a wearable device that can control them, measure them on a person. The aim of all this study, of course, is the creation of a safer HMI systems that can lead to a reduction of the accidents and of the risks. So thank you for your attention, and if you have questions, ask me.